All right, I think I will go ahead and start 2 minutes in. So I just want to say hello and good morning to all of our attendees. Thank you for attending our Live from the Labs webinar. Today, we will be talking about the classification of botanicals using MALDI-TOF MS combined with multivariate analysis. Today, you'll be hearing from Mark Arnould, live from the Bruker lab, and Christian Krueger, live from the Complete Phytochemical Solutions lab. Mark Arnould is a senior application scientist within the Applied Markets division at Bruker. With a concentration on polymer applications, he has over 20 years of experience analyzing synthetic macromolecules using mass spectrometric methods. Christian Krueger is the CEO of Complete Phytochemical Solutions. He has a career spanning over 25 years as a principal investigator and phytochemist, specializing in the development, validation, and harmonization of mass spectrometric methods of the authentication of dietary ingredients. All attendees will be on mute for the duration of the presentation, which will end with a Q&A. Please feel free to use the chat and leave all of your questions there. I will be watching it and answering as we go along. Now I will pass over the podium to Mark Arnould.
Thank you, Megan. Hey, everybody. This is live from the lab with Bruker. I'm here in the beautiful demo lab in Billerica, Mass. Today, we're going to be going over with Christian from Complete Phytochemical Solutions, the classification of botanicals using MALDI-TOF MS combined with multivariate analysis. So the basic outline of what's going to happen today is we're going to have an introduction to matrix-assisted laser desorption ionization, time of flight, mass spectrometry, the instrumentation, and the workflow. We're going to briefly go over the Bruker MALDI-TOF instrument portfolio, and then Christian from CPS, again, will do his live demo from his lab, and then that'll be followed by a Q&A session. So first, why MALDI-TOF? It's simple, it's easy to operate, fast implementation. Once a method's developed, you can start generating data immediately and increase productivity. It's fast, there's minimal sample prep, there's no chromatography, drastically reducing turnaround time. And again, productivity goes up with time per sample going down. It's accurate, it's high resolution, exact mass measurement, increasing specificity of target molecules, and also unequivocally assigning formula to unknown masses in your sample. It's flexible. We could do soluble, insoluble analytes, tissue imaging, synthetic macromolecules, and natural materials. So if you can get it onto the target and get it in the instrument, you could probably generate some data. It's comprehensive. So whether you're doing routine targeted QA/QC, advanced non-targeted analysis, so whether you're looking for batch-to-batch variation or trying to single out a molecule that could be giving you problems, Bruker probably has a platform that will help you out. So now we're going to get into the workflow. Basically, how does MALDI-TOF work? Well, the first step is sample preparation and introduction to the instrument. So no matter what we're analyzing, we have to get it onto a stainless steel target or some other target that fits into the Bruker instrument. Here's an example. So there's two main ways of introducing sample into the instrument. On the upper right, you can see here that someone is using the dry drop method, which is basically dissolution of your matrix, analyte, and salt, the combination of these three into a specific ratio, and then depositing a small amount on the target surface to dry. On the bottom right, you could see that we could also do a solid sample prep. For LDI, you could just smear a small amount of your analyte onto the target surface, leaving a thin layer, cleaning it off, and introducing that into the instrument. Or you could combine your solid analyte with your solid matrix, and then maybe some cation, and then mix those together on the target surface, leaving a thin layer, and then getting off of, blowing off the rest of the powder and putting that in the instrument to generate a spectrum. So once you get your sample into the instrument, you insert the target. So you could watch the camera feed. I'm going to zoom in on the instrument, and you could then change the windows in the webinar to view the video or view or stay on the presentation. So this whole process is automated. So it goes from atmosphere to lock to source very fast, and it's, you know, easy and simple to do. Once the target is inserted in the source, you're ready to start driving the instrument. So give me a moment and I'll insert the target. Okay, now that we have the target in the source, here's a small video that is an example of someone actually operating the instrument. So this is what you would see as an operator or be doing as an operator. So we can see here, once the sample is inserted, you can have a real-time zoomed in view of the sample target. You can move to any position on the sample target with one click, as long as you know where your sample is, letter, number. And then once you see your spot, you can then one click choose your parameter files. That will update the instrument with all of the settings, laser, voltages, and everything. Then adjusting in real time your laser power. You find a good spot on the target and you start acquiring data. And then you can adjust your laser power as needed to maximize signal resolution, peak shape, or shape of this overall distribution of this polymer, to where it looks like it's representative, or you feel it's representative of the sample just above threshold irradiation. Once you're happy with the data, you could then start adding it into a sum buffer, and you will see a red spectrum come up behind this blue spectrum, which is the sum of all the signal that is acceptable to the user. And then once you're done collecting your data, you give it a name, type in any other pertinent information, and save this file. And you can see that generating a mass spectrum is in the order of seconds to minutes from start to finish. So that's what you would see on the outside of the instrument. So the MALDI-TOF process, if we could slice the instrument open, this is what you would see on the inside. So this is a two-step procedure. Samples are fixed in an excess of crystalline matrix on the target surface. And in the first step, ionization. The matrix and analyte are bombarded by a laser and vaporized into the vacuum. During this process, the molecules become ionized, and then HV being applied accelerates the ions out of the source and into the flight tube. The second step is the TOF MS phase. In the linear mode, ions will impinge upon the linear detector in nanoseconds after ionization, with higher mass molecules arriving later than lighter ones. Flight time measurements make it possible to determine molecular masses directly. Each peak in the spectrum corresponds to a specific mass of the ion along the time axis when you start measuring time at the moment of ionization. In the reflector mode, after this is done, in the reflector mode, the ions are diverted towards a second detector, extending the flight distance and focusing the ions. The combination of these two effects generates higher resolution spectra than in the linear mode. And this resolution gain is accomplished by the reflectron, which you just saw, which is an energy mirror, decelerating and reaccelerating the ions towards the reflector detector. And now we have our basic, instrument portfolio, and the take-home message here is one size doesn't fit all. Whether you're doing routine QA, QC, monitoring batches, we have a benchtop instrument available. But as your research or instrument needs change, you could get to faster and faster acquisition, and then higher molecular weight range with faster acquisition in MS-MS mode, And then at the end, you have the ultimate in speed for tissue imaging and super high throughput. And with that, I will turn it over to Christian, who will proceed with his live demo.
All right, thanks, Mark. Can you see my screen here?
Yes, we can see it.
Okay, great. I want to make sure that I'm sharing this properly. Give me just a second here to get this set up, as these displays always become complicated. Okay, thanks everybody. Picking up from where Mark left off, let me get this out of the way. How to get rid of this?
We can see your screen fine, Christian.
Okay, you can't see any of the other stuff sitting over the top of it?
No.
Okay, good. I can, unfortunately, but that's not anybody else's problem. Let me get started here with a quick overview of what we'll go through here today. Give you a quick introduction to Complete Phytochemical Solutions, who we are and what we do. Talk a little bit about the quality control issues in the decision making on procurement of good quality ingredients, botanical ingredients, and the qualification of unique formulated products. And this could be formulated blends and all the way up to a retail finished product. We'll talk about MALDI-TOF being a fit for purpose for analytic identity, and then talk about multivariate analysis for the categorization of botanical ingredients, and then finish with a summary. So a little bit about Complete Phytochemical Solutions. We are a contract research organization and provide third-party analytics service. So we work across the continuum of supply chain, from the growers, these are the folks that could be producing the fruits, vegetables, forages. We work with formulators, those that buy ingredients and blend those in proprietary processes, and then final retail products. Could be functional foods and beverages, dietary supplements, things of that nature. What we offer is a package that we refer to as polyphenol fingerprinting, and this is really a collective of analytic methods and instrumentation that support the identity testing or authentication of botanicals and finished products, a platform for the standardization of the content of the botanical products, and then finally an efficacy evaluation. Do these products actually promote a health outcome, either in animal or human nutrition? So today we're going to talk a little bit about how MALDI-TOF can serve as one of the pedestals of the analytic platform to support the identity testing or authentication of products. So there is a challenge in the industry, and that's how do you identify a heterodispersed oligomeric polyphenols? And as Mark showed in his demonstration earlier, he had a polymer dispersion that was a synthetic polymer dispersion, but nature produces polymers as well. And so if you think about things like a chain, nature produces these compounds of polyphenols that are connected one building block upon building block. And the interesting thing about this is that each plant follows a general roadmap of what a polyphenol looks like, but they make unique modifications. So for instance, the polyphenols in cranberry are different from grape, and they're different from blueberry. So there's a unique fingerprint to each botanical. And so there's a need for a high resolution analytic platform that's fit for purpose, that can handle the complexity of the oligomeric polyphenols. And our solution that we're going to discuss today is the use of MALDI-TOF mass spectrometry to support the identity testing. As many of you can see from this image, it's pretty easy to tell the difference between a cranberry and a grape or a grape seed or even pine bark. And all of these are used in natural product formulations. And if you took a slice of these and put them under a microscope, you could see that there's unique botanical structures that can be identified. So it's relatively easy for the naked eye or with the assistance of microscopy to identify an intact fruit or botanical product. Where it becomes more difficult is when these various botanicals are extracted and enriched in certain classes of polyphenols. And in our case today, we'll be talking about proanthocyanidins. But most of these then come out and look like this poorly defined brown or brownish red powder. So it would be very difficult, even with microscopy, to tell the difference between an extract of grapeseed extract, cranberry, or pine bark just by its physical look. We'll give you a quick introduction to proanthocyanidins. I've mentioned this a couple times during the introduction. This is an example of an oligomeric polyphenol. Another example would be hydrolyzable tannins. These could be found in fruits like pomegranate, raspberries, and strawberries. But the proanthocyanidins are an oligomeric series of repeating catechin units or epicatechin units. And if you look here, there's a common structure. Here's one catechin unit, here's a second, and here's a third. So each of these then, as we add them, add a degree of polymerization. So the structure can vary in degree of polymerization from a dimer up to in excess of probably 50 mers or greater. And again, the unique thing about MALDI is that it's well suited to handle the complexity of all of these variables that we'll be talking about. The second thing is the substitution of the ring structures. So in this case, we see that there's a couple hydroxyl substitutions on this particular ring. This can vary as well from botanical to botanical. There may be 1, 2, or 3 hydroxyl groups. And as you'll see later in this presentation, there's also modifications of other locations on the ring structure that can include sugar moieties or the esterification of compounds like gallic acid. And then we also have a variation in the nature of an interflavan bond. And what we're talking about here is how are the two building blocks connected? So if these two blocks are connected through a carbon-carbon linkage, we refer to that as a B-type linkage. If the two adjacent building blocks are linked through both a carbon-carbon link and a carbon-oxygen-carbon link, that's referred to as an A-type bond. And these are the two structural variations that we're going to be paying particular attention to as we look at our data sets today. And these will be the hallmarks that help us differentiate and classify our botanicals of interest. I can say that this class of compounds is very challenging when it comes to colorimetric, HPLC, and HPTLC analysis. And for that reason, we've developed MALDI-TOF mass spectrometry methods for the characterization of this class of compounds. And much of what I talk about today is going to be based on this AOAC first action method, in which we describe a MALDI-TOF method for the identification of cranberry proanthocyanidins, and specifically A-type proanthocyanidins. But suffice it to say, the instructions and the methodology in this particular publication can be applied to a wide diversity of botanicals, not just centric to cranberry. As Mark pointed out earlier, what we do is we take a sample and in this case, the samples are the little red dots here. And we deposit them in combination with a matrix. In our case, we're using dihydroxybenzoic acid as our matrix. And we mix those in solution, apply a drop, and allow that to dry on the stainless steel target. That target is introduced into the MALDI-TOF instrument, as Mark showed, and impacted by a laser where the compounds of interest are desorbed and undergo an ionization event. And in our case today, we'll be looking at the positive mode or positive ions that are produced as part of this process. Once again, it's a soft ionization method. There's a uniquely less multi-charged ion. So if you think about and have experience with electrospray, very often you're looking at multiple charged species. In MALDI, we're usually looking at a singly charged species. And this makes interpretation of the data much easier, so we don't have to worry about multiple charges stacking on top of each other. Right now, what I would like to do is switch over to the MALDI control and show you just how easy it is to acquire a data set in real time. And then we'll do a little bit of work in the Flex Analysis software package to show you the interpretation of the data. And then I'll come back into this PowerPoint presentation. So let me escape this and then switch over to our Flex control here. And hopefully everybody can see this now.
Yeah.
What I've done is I've deposited a standard, a reference standard. This is a cranberry reference standard, and it's on the target, and stainless steel target, in position A6. And all I'm going to do is hit the start button, and what we're going to do is we're going to acquire 2,000 shots of this. So the laser is going to pulse 2,000 times and come up with a data set here for us. There we go. And right now we have a very low laser intensity, and we can see that we're not getting a lot of peaks of interest. So what I can do is show you just how quickly we can adjust the laser power and reshoot this sample. And now we see this real beautiful oligomeric series of trimers, tetramers, pentamers, hexamers, heptamers resolve. So very small changes in the operator's environment can quickly resolve these compounds from baseline noise. I'm going to switch to the Flex Analysis software. So once the data has been acquired and saved, we come into a second software package where we can actually inspect the data with a little bit more intensity here. And so here what I've done is I've labeled each of these peaks of interest. And again, this is a proanthocyanidin trimer, tetramer, pentamer, and so on out through the polymer distribution. And in this window, we can actually zoom in on any of these polymeric series, and we can see that there's additional masses of interest. So for instance, this particular mass here, if we can label this, is 16 mass units heavier. And as I discussed earlier, that's an example of how there's a potential additional hydroxyl substitution occurring on that ring structure. So the molecular weight of oxygen is 16, and we would expect to see a 16 mass higher compound. And then we can also see within this that there's 2 mass unit differences. So I'm going to label just one more mass here in this environment. And that's the mass of 1173 versus 1175. This is the difference between B-type and A-type linkages. So again, in the formation of that A-type linkage, you're losing 2 hydrogen. And so the loss of 2 hydrogen gives you a compound that has a mass that is 2 atomic mass units lower. And so with this information, we can go into a further inspection and into what we're going to call a deconvolution and multi-component analysis to see how these unique fingerprints can help us characterize and categorize the botanicals that we're working with. So I'm going to exit this window again and get back into the presentation. Let's see here, I'm gonna move this out of the way. Okay, hope everybody can see that. We're back in presentation mode.
Yep.
What we're talking about here now is the A-type and B-type interflavan linkages. So I'm going to start with the very simplest proanthocyanidin, and that's the procyanidin dimer. In this case, we have a catechin attached to another catechin through an A-type linkage. And this compound has a monoisotope, or the most abundant isotope, of 599 atomic mass units. By comparison, the B-type dimer has a monoisotope of 601, and that's due to the fact that there's 2 additional hydrogens. So if we break this bond here, we're going to pick up 2 additional hydrogens, and this compound is going to appear as 2 atomic mass units heavier. So what becomes really interesting is if we have a 50-50 blend of a dimer with an A-type linkage and a dimer with a B-type linkage, what we end up with is overlapping isotope patterns. So this isotope distribution of the A-type overlaps at this, and this location with the isotope distribution of an all B-type dimer. And because these isotopes are naturally abundant and predictable, if we have 2 compounds that overlap one another, we can deconvolute those overlapping isotope distributions. And we do that through a process of matrix algebra. And I won't go into the details of the matrix algebra. It can be found here at the publication by Feliciano et al. But suffice it to say that we can solve 2 or more simultaneous equations at once to get the relative percentage of A-type to B-type interflavan linkages. So in this case, we know we blended 50% A-type and 50% B-type, and our prediction comes out to 49.7 and 50.3. So we have a very accurate prediction of the blended overlapping isotope patterns after applying a deconvolution matrix algebra algorithm. So what we did next is we validated this deconvolution, and we said, well, let's look not only at a 50-50 ratio, but let's make 11 different ratios, going all the way from a 5% A and 95% B to the opposite, 5% B and 95% A. This is incorrect. This should be a 0 here. And we found out that our estimated values after deconvolution are within 3% of our predicted values. So not only have we established a tool for identity testing, but we also can look and use this tool for unique formulations and percent of blending of 2 proanthocyanidins. And what we really then have is a semi-quantitative mass spectrometry application. So that was real simple, right? We took a standard, a dimer, A2 dimer standard and a B dimer standard and blended those together. So let's go into a real world scenario in which we take a more complicated distribution, one in which we isolated the proanthocyanidins from cranberries and blend those with isolated proanthocyanidins from apples. In principle, at each degree of polymerization, and again, this can be from the dimer up through the decamer, so 1 to 10 or greater degrees of polymerization, we're going to see an overlapping isotope at each of those degrees of polymerization that corresponds to the unique fingerprint of each of our botanicals. And if we show this graphically, what we can see is that in the instance of cranberry, we have predominantly 1 or more A-type linkages and very little all B-type. So the all B-type is the purple. Okay, so we see that less than 10% of the proanthocyanidins at any degree of polymerization is all B-type. Whereas in the case of the apple, predominantly greater than about 85% is attributable to an all B-type procyanidin oligomer. So these have two very distinct fingerprints. If we do something very similar to what we did with the procyanidin dimers and blend these two isolated proanthocyanidins at 21 ratios and look at the degrees of polymerization between 3 and 8, we can see and once again be very accurate in our expected versus observed ratios. In this case, we're within 4% of our expected blends. So again, a very powerful tool for looking at two heterodispersed oligomeric polyphenol series from cranberry and apple. So next we moved on to looking at different fruits. And in this case, we looked at apples, black chokeberry. We actually looked at coca powder. Coca also and chocolate contain proanthocyanidins, cranberries, and grape skins. And what we did is we called in the A and B ratios observed after deconvolution and MALDI acquisition into a principal component statistical package. And what we're seeing from this is that our cranberry fruits, for instance, have a very clear segregation away from fruits like apples, grape skin, and coca. The cranberry products here also are very closely aligned with the cranberry fruits. So these products are juices and products like sweetened dried cranberry. So this is an example of a principal component analysis in which the cranberry products are being classified in this region away from other products that are being classified in this region. And again, this is a very supervised environment. We're only calling in the A-type and the B-type ratios to make this differentiation. One further example of this is a comparison of cranberry, once again, categorizing in this location, to apple proanthocyanidins, categorizing in this location, and peanut skin proanthocyanidins, categorizing in this location. And then what we did is we blended, again at different ratios, either cranberries with peanut skin packs or cranberries with apple proanthocyanidins. And you can see that each of these blends categorizes into their own distinct region or location. There was a cleaner separation of apple and cranberry proanthocyanidin based on A to B ratios than cranberry and peanut skin. So there's a lot of overlap in this location here. But suffice it to say, we were still able to segregate away from the 100% cranberry and the 100% peanut. And so again, this is an analytic approach to call in very complex data sets from MALDI-TOF mass spectrometry into statistical programs, principal component analysis platforms, for the purposes of segregating and categorizing the compounds or botanicals of interest. And in both of these cases, in this case, these two principal components explain over 90% of the difference between these two, these 1, 2, 3, 4, 5, 6, these 6 groups. And in this case, the two principal components, again, are very close to 90% of the explanation of what's separating these two classes. So I think it's important to just come back to this this method. If anybody's interested in learning more about this application, here's a great resource. We are really and have been talking about a supervised data set. And what I mean by supervised data set is that the analyst is making the decision of which particular peaks are labeled, how those peaks of interest are manipulated. In our case, we're subjecting them to deconvolution and establishing the relative A to B ratios. And then we're calling that data set, that very controlled and supervised data set, into a statistical package for principal component analysis or multivariate analysis. Where we would like to move and where our research is going at this point is toward a more unsupervised data set. So as I mentioned earlier in the introduction, in addition to substitutions on the ring structure with hydroxyl groups and the nature of the interflavan linkages, A type or B type, there are also other opportunities for substitutions on the extending units. And so the example with grapeseed extract is that there's a gallic acid that can be esterified at this position. This esterification leads to another polymer distribution. So here's our procyanidin, trimer, tetramer, pentamer, and here's the trimer with a gallic acid, the pentamer with a gallic acid, and the hexamer with a gallic acid. So here we really have two unique polymer distributions that are integrated into one data set. And so this information, these intermediate gallic acid moieties, are also suitable to be called into a statistical package. And again, if we call those in on purpose, we're going to be supervising the environment. If we were to say to the statistical software, let's just call in the XY data, and I'm going to let the software itself determine across this whole diversity what are the most relevant components or the most relevant masses to differentiate, we are now moving toward an unsupervised environment. And this can be a very powerful platform because we're looking at multi-dimensional comparisons. Graphically, when we present this as an image like this, we're only showing two dimensions. We're showing the X and the Y dimensions. But in statistical packages, you can have higher level dimensions that aren't capable of being captured graphically. And that's really the power of an unsupervised approach. Just one more example, and this is kind of a real life application in which we're looking at pine bark proanthocyanidins. Again, pine bark has the proanthocyanidin series we saw previously, and in this case it has a unique intermediate. There's a pentose attached to the polymer, so we have intermediate masses that are associated with 132 atomic mass unit differences. But the real take home here is that if we have a reference standard, this is purified proanthocyanidins from pine bark, we can use that reference standard to look at production lots of an industrial manufacturing process and compare lot 1, lot 2, so forth and so on to the standard for continuity. So again, this is the unique hallmark and what needs to be substantiated in both the ingredient, the selective extract, and in the final finished product. So MALDI-TOF, again, is a great platform for supporting identity testing of complex oligomeric polyphenols. So I'd like to just quickly summarize what we've covered here today, and that is MALDI is a fit-for-purpose analytic platform for heteropolymeric compounds. And this can include things like oligosaccharides as well. So while we focused on proanthocyanidins today, we can apply this to foods, beverages, and dietary supplements, look at proanthocyanidins, hydrolyzable tannins, oligosaccharides, Even some of the smaller molecular weight monomers, such as anthocyanins and flavonol glycosides, are suitable for analysis. And I'll mention that we're doing a lot of this work in collaboration with the American Botanical Council, United States Pharmacopoeia, AOAC International, and also most recently we are working with the USDA in a cooperative research agreement. So with that, I'd like to thank all of our team here over the years. I certainly have not done this work by myself. I think I've covered about everybody I can think of on this slide here, but to those I didn't include, thank you for all your time and effort to advance this science. And with that, I'm going to come to completion, and thank you for your time.
Thank you, Kristen.
Thank you both to our speakers. Appreciate your time and your efforts and your presentations. I want to remind all of our attendees that you can put a question in the chat. We have a few here that I'd like to go through. All right, what is the laser energy you are using?
I'm assuming that's a question for me, and that is really has a lot of variables. So I would say generally we're somewhere in the range of a laser power of 60 to 70, but the laser power, and I'll let Mark address this as well, is really quite unique to the instrument, the age of the laser, and the nature of the analyte and matrix that are being laid down. So in our particular case with dihydroxybenzoic acid and oligomeric polyphenols on our Autoflex Max Bruker instrument, we're in that 60 to 70 laser power region.
Right, there's no set laser power, so you want to use enough laser to desorb and ionize the molecules, but not enough power to fragment them. So it's called threshold irradiation. You want to be just above threshold, and that's different for every setup and depending on what you're analyzing and the molecular weight range you're looking at.
All right, next question. What is the mass range of the Autoflex Max?
I believe it's up to 300,000. You could probably go a little higher, but reproducibly, I would say 300,000. And then if you wanted to go to higher and higher masses, you would probably want to purchase or use a larger instrument with a longer flight tube and greater acceleration, better detectors.
Thank you. Can you use this for other botanicals?
Yes, quite simply the answer is yes. We work with a wide range of botanicals. We've looked at fruits like aronia, raspberries, strawberries, blueberries, cranberries, just about anything you can think of is likely to be suitable to the mass spectrometry, the MALDI platform. And again, it doesn't have to be centric to oligomeric polyphenols, although that's most of what we've discussed today as a challenging class of compounds. The lower molecular weight compounds, the hydroxycinnamic acids, the flavonols, the anthocyanins, are also really easily detected and ionized in a MALDI platform.
Thank you. Can you do MS-MS with MALDI?
Yes, you can isolate a particular compound and either do MS-MS just by using the laser power, so increase the laser energy to impart internal energy to cause the molecule to fragment, or you can add a collision gas with a high center of mass energy, which would then, bounce off, then the analyte molecules would then bounce off of that, transferring energy and causing fragmentation.
Excellent. Next question. Is there an official AOAC method in place?
So the method that I referenced was a first action official AOAC method. At this point, there is not a method in the official methods annuals. We're working right now with cooperating laboratories. The AOAC process is one in which you need to go through multiple labs for a validation of the particular method. So our first action method was published in 2021, and we're working toward the engagement of additional laboratories to support a pathway to an official OMA.
All right, almost at the bottom here. What is the expected life of the laser?
There is no lifetime that I know of. I mean, I guess you could probably look it up for a neodymium YAG laser, but it's all about application. If you're using just the instrument for QA/QC, taking a few laser shots, depending on which instrument you have, nitrogen lasers go bad faster than the neodymium YAG on the rest of the instruments. But if you're just doing basic QA/QC, few thousand laser shots or 10,000, 20,000 a day, it could last a very long time. But if you're doing something like imaging, tissue imaging, where you're firing the laser tens of thousands, hundreds of thousands of times a day, it won't last as long. But my own personal experience, I've had several Bruker instruments, and both of my lasers on both platforms were upwards of 20 million shots, and the lasers were still going strong.
Yeah, I might just follow up with that, Mark, because you hit on something that was really interesting, and that's imaging, and that's something we haven't talked about. But I showed in my presentation that a macroscopic examination of a slice of a cranberry, for example, would help in identity testing. And with these instruments, you could actually take a slice of a fruit or other biologic tissue, place that on a target, and introduce that into the MALDI platform or into the MALDI instrument and image that. So you're raster scanning with your laser across the surface of that biologic tissue and looking for unique masses of interest. And so this can be very interesting when you think about location of particular phytochemicals in our application. Would the proanthocyanidins, for example, be isolated in a unique vacuole within a portion of the cranberry? Would the anthocyanins, for instance, be isolated in a location? If you slice a fresh cranberry open, the red pigmentation is only on the outer layer. The center of the cranberry is white. It's only after freezing and kind of going through a thawing and processing that red pigment bleeds through the entirety of the cranberry. So again, MALDI has, beyond just the applications that we demonstrated here today, it has the power to do imaging, which is really unique for a mass spectrometry instrument.
Right, and then also you'd have to change platforms. The Microflex can't do imaging, but as you move up to more and more, the Autoflex Max behind me or behind Christian, then you could start getting into imaging. And then the faster the laser, the faster you could turn around these samples. So with these types of instruments, depending on the size of the image, it could take 12 hours to raster the whole thing. But if you move up to the Rapiflex, where you're firing at 10,000 hertz of the laser, then you're decreasing your experiment time to just hours.
Mm-hmm. Oh. And I might just make one more comment while we're, I hope we got enough time here, Megan, cut me off if I'm yakking on. But there's also interfaces that would enable a TLC plate or an HPTLC plate to be introduced into the MALDI. So again, if you're using HPTLC for separation chemistries, that plate could be physically mounted, and again, Mark could explain, the apparatus, but that too can be introduced into the MALDI, and in a similar manner, you can liberate the compounds of interest and ionize those and get a mass spectra from a HPTLC plate.
Right, Bruker sells different targets for mounting different slides or TLC slides, so we can mount ITO slides on a target holder that holds 2 for tissue imaging or other, if you could get your sample affixed to the ITO slide and get it in the instrument, you could probably generate an image from it, but there's other holders as well for TLC plates.
All right, I have a couple more questions here, and we have just a little over 5 minutes left. How tall is the Autoflex Max? Their lab is about 8 feet tall, so they're curious about size restrictions.
I don't know that offhand. I could go stand next to the instrument. I'm 6'2", so if you want to guesstimate.
I believe it's around 7 feet tall.
Very nice. A mark comparison.
I think it'll fit in an 8-foot ceiling. So
Another question, how much is the Autoflex Max?
that is a question for somebody in sales. I have
Yes,
absolutely
yes.
no idea.
It's around $280,000, depending on if you had MSMS capabilities.
Thank you, Brian. Appreciate it. What are the power requirements for the Autoflex Max?
I believe it's 220.
All right,
correct.
and our final question, what is HPLC?
TLC.
Oh, great.
HPTLC.
So yeah, there's two things. So HPLC would be high performance or high pressure liquid chromatography, and HPTLC would be high performance thin layer chromatography. And that's really based on some of the original separation technologies in which a plate is covered with a solid phase resin, either normal phase or reverse phase. A sample is spotted at the baseline of that plate, and a solvent migrates up through the plate, carrying and separating the compounds of interest. So HPTLC would be the newer version of a TLC plate.
Excellent.
So Christian, do we have time for one scientific question?
We do. This
Absolutely.
looks like the end over on my side. So we have about 5 minutes left.
Just out of curiosity, when you were showing the oligomers, I can't remember what they were called, but are those protonated, sodiated ions that you're observing?
Great point. Everything I was showing today was shot with whatever was naturally abundant in the environment. So it's interesting that the proanthocyanidins will choose to pick up both naturally abundant sodium and naturally abundant potassium.
Well, that was
And
leading into my question. Your plus 16 peaks may not be from being oxidized or an extra oxygen. It could just be the naturally occurring 16 Daltons that you would gain between sodium and potassium. So I was wondering how you would tell the difference between those.
Right, you're correct there. So to resolve that conflict, what we do is we deionize the sample. So once it's in solution, we mix the matrix and the analyte together, subject it to deionization with a cation exchange resin, and then we spike it with cesium. So the cesium will shift the entire mass spectra 132 atomic mass units, and that resolves then any 16 mass unit differences. If a 16 mass unit difference is still detected, it has to be attributable to an oxygen. It can't be sodium and potassium. And that, I believe, in the AOAC method is described as well as the deionization process and the spiking with cesium. So today for the demonstration, it was just environmental, but we can control the nature of that cationization event.
Nice.
We do have one more question coming in. Is there any special requirements for their TLC?
I do not myself run TLC plates on the instrument. Mark, maybe you can answer. It's probably a size limitation as to what can be introduced.
If they're talking about getting into the instrument, yes, the holders only hold a certain size of the TLC plate, or like I said, ITO slides. If it's another question about how they're doing their TLC, I wouldn't know the answer without more specific points.
All right, that looks like the end of our chat box. If there are no further questions, I'd like to thank our presenters again and all of our attendees for coming to our webinar today from both the Bruker lab and the CPS lab. And with that, I'd like to tell everybody to have a nice day, and thank you very much.
Thanks, Megan.
Thank you.